All right, here we go. Section 8.4, partial fractions. This is a short and sweet video. I wanted to just indicate to you why we're doing this. We've got three methods that you've learned so far on how to find antiderivatives. None of those would fit with this antiderivative right here. Okay? This particular one doesn't fit formula, doesn't fit u sub, and it doesn't fit parts. So we go to a method for finding antiderivatives using what we call partial fractions. Okay, so normally these are pretty easy to spot. In fact, they're always easy to spot because you normally would get a linear polynomial in the numerator and a quadratic polynomial in the denominator. Okay, and so we're just going to basically take this fraction and we're going to rewrite it using two simpler fractions, each of which would be easy if they were in the integrand. Okay, so we're going to take one integrand and we're going to make two, both being linear, and so that'll be pretty easy. Okay, so that's the first step, and if you ever hear the term non-repeating linear factors, that's what this means. Non-repeating linear factors. It doesn't really matter, just follow along here. There is a shortcut for this method, for this partial fractions method, which we're going to get to in a couple minutes. In fact, I'm going to go pretty quickly through this first method, which I would encourage you to not use. I'm going to encourage you to use the second method. But if you want to pause and rewind the video or whatever, if you like the first method first, go for it. Either way, you're going to get the same answer. So the first method would be multiply by the common denominator, get rid of the fractions, and then this here, basically what you're going to do is you're going to break it down and you're going to set up two equations with two unknowns. And like I said, I'm going to go through this pretty quickly. This is not the method I would use. So we have two equations, two unknowns, which would be pretty easy to solve. And I wanted to pause it when we get to one certain spot. When we finally get b, okay, so b is 2, a then would be 3. So you found the constants a and b, you took the integrand, and you rewrote it so that we have, instead of the integral of one fraction, we have the integral of two fractions, which we can even break that down even further. The integral of a sum is the sum of the integrals. So I want you to think to yourself, in fact, I want you to pause the video right now and see if you can figure out, if you can remember, what the antiderivative of this integral would be. Okay, what would the antiderivative be? So pause the video, I challenge you to get that. And if you came up with that, then you're right. Okay, so again, partial fractions. If we talk about partial fractions, this is the only way to do it. As far as it's not going to look like you're not going to have a different method. This is the partial fractions method. I don't know what I just said. I'm just got a dose of medication, so cut me some slack, okay? So there's a shortcut, and the shortcut is what I actually call the convenient values method. We start off the same way, and then I don't know if I mentioned this or not, but this particular equation right here is what we call an identity. This equation is true for all values of x except, well, it's for all values of x. So you can pick any value of x you want to and plug it in for x. Okay? In fact, think to yourself, what maybe this is something you're thinking, well, what if I chose 0? Well, if you chose 0, then you'd still have two unknowns in there, right? Neither of these a or b would go away. But if you choose -1, that's a convenient value. So if you choose -1, look what happens. The a goes away because then -1 plus 1 is 0. And so since the a goes away, you just get -4 times b is equal to 8, and we get b is 2. Okay. Now you could plug it back in and solve for a, but there's another convenient value. The other convenient value would be x equals 3. So you plug 3 in for x, the b goes away, and you get a times 4 equals 12, and you get a equals 3. Okay, that's it. And then you rewrite the integrand, just like we did, and we have the answer. That's the antiderivative. Now, if you were hoping for 2 or 3 or 4 more examples, I'm sorry to tell you that I'm done. And I've got a worksheet that you should have seen already, and the answers are, I don't know if I included the answers on the Canvas site, but either way, print out the worksheet, bring it to the next class, and you guys can work together. And I can't remember which ones I want you to do, but I'll figure it out. I'll let you know. And then that's it. That's the partial fractions method. So I hope you understand, and send me an email if you don't. I'll try to clarify anything, or send me a message through Canvas. Have a great night, and again, guys, thanks for the messages. I have not seen the doctor yet, so I don't know yet what the next step is, but I appreciate your prayers and thoughts, and I will see you soon.